Welcome back, everybody. Try to find a seat. There's definitely seats over here, so let's not sit on the floor if we can find seats, like over there. Yeah, the fire marshal's going to get me. Actually, I saw a fire in the Oakland Hills when I was driving in. I hope, hopefully, this building will still be here next week. So, last time we talked about threads and implementation, and one of the things we talked about was the state that's unique with threads. And there's a seat back over that way. Basically, threads have, for instance, CPU registers, program counter, pointers to the stack, all that sort of stuff. Scheduling info, which we're going to spend a lot of time talking about in a few weeks. Accounting info, pointers, so on. Maybe a pointer to the enclosing process. And this is one of the things where in your project you're probably going to end up modifying the thread control block. You'll probably put stuff in there as part of what you do. The operating system then keeps track of thread control blocks, as I mentioned, in a whole series of queues. And the key, sort of the king among queues, is the ready queue, which is these are all the thread control blocks that don't have any pending conditions, and they're just waiting to get CPU time. The rest of the queues in the system are all pretty much wait queues. They're places you put TCBs temporarily when they can't run because they're waiting for something. So they might be associated with a disk, with the network. They might be associated with another thread if you're joining with that thread, for instance. We'll talk a little bit about that later. The other thing we talked about was we started diving into the implementation a bit, and we talked about this notion of yielding. And yielding can either be done explicitly with something called yield, or through various types of implicit yields, like you try to do some I/O. You've just yielded the processor. You wait for a signal. You've just yielded the processor. So anytime that you go to do something that waits on something else, that's an implicit yield. Or if you actually execute yield, okay, you've also given up the processor at that point. And so far, this is the primary way that you've seen for threads to become multiplexed. So if we've got 12 threads in the system, hopefully they're all yielding regularly. Otherwise, you don't make forward progress on some of them, and a thread could actually take control. And that's basically the way a lot of early personal computer systems worked. They all had the notion of yield. It's still the way that a lot of windowing systems work. So anybody here ever programmed X10 or maybe Microsoft Windows apps where you're actually putting up windows? Anybody? Okay, sorta. So, you know, there you got to be extremely careful because you can actually lock the windowing system up if the primary thread associated with the window doesn't do the right things on a regular basis. Now, the stack for yielding was a pretty interesting thing, which was the beginning of our sort of discussion about what's going on. And what we showed here, for instance, was some routine like compute pi that yields every digit. That was kind of an example we gave. And what happens when it yields is it first traps into the operating system. And why do we have to trap into the operating system here? Why do we have to go from blue to red on my diagram? Does anybody remember? Okay, what sort of privileges? Okay, yeah, privileges, something about privileges, yeah? Okay, so we actually haven't really talked about processes. Right now there's one process in the world, and so we don't really need to do that to change processes, but we will, by the way, soon. So good answer. What else? So privilege is kind of the right track here. Go ahead, yeah? User mode, kernel mode, yes, and what about kernel mode? Can you speak up a little? I can't hear you. Yeah, I mean, you're all kind of dancing around. Oh yeah, one more, go ahead. You need to change the stack pointer, and only the kernel can do that. So that's a good guess, but not true. I'm actually, because it's a register like any other, so in fact a user mode process could screw itself up by putting a bad stack pointer in if it wanted to, and nobody stops it from doing that. So in fact, I'm kind of leading you guys in a red herring direction here, no pun intended, but the thing to realize is up till now, it's the kernel that's actually multiplexing the threads. The thread control blocks are stored in kernel space, the way we've been describing them. Okay, and so the only way to actually get at the threads which are stored in kernel space is by going into the kernel. Now, at the end of the lecture, I'm actually going to talk about user mode versus kernel mode threads, and you can do threading entirely at user level if you want. Okay, and so nothing that's involved here in the switching of threads has to be kernel mode because it just involves registers. Once we start switching processes, then that's got to be in the kernel because we're changing address spaces, protection. Okay, so let's go back on this. So how do we run a new thread, which is basically picking something that has to run? We basically pick it, and that's the scheduler that we haven't talked about yet. We switch registers from one for the other. We do some housekeeping, which we'll talk about later, and we're good to go. And how does the dispatcher do this switch? Well, it says anything the thread may trash, the next thread may trash, like the PC's register stack, and loads in from the other one. Okay. Any question on this so far? We're going to get to that little horseshoe diagram that I'm sure not everybody's digested yet. Yes?
We want to save the program counter, but what is this code? Will it use a different program counter? And how are we going to make sure we don't, as we execute this, we don't override the program counter?
That is a great question. How do we get the program counter when it looks like we've screwed up the program counter because we've trapped into the kernel is what you're worried about?
Or just executing code.
Executing code. That's a great question. Can anybody answer that question? Yeah.
Will it get saved into a return address register when you jump into the kernel?
So yeah, so first of all, when we jump into the kernel, the actual return PC is stored in a register. But actually that's not, so that's a good answer, but it's not quite the full answer. Let me give you the full answer. In fact, it's the PC down at switch that we care about, because what we're going to do is we're going to save the PC for this when we switch to somebody else, and then when we come back to this, we'll have the PC to return, and our return path is actually returning out of switch into run new thread and returning back up and then returning to yield. So, okay, and that's part of this horseshoe diagram I showed you guys last time, which we're going to make sure you all get. Okay, so here it is, the two-thread example. Now, again, we haven't started threads yet, so threads exist right now. This is steady state. They've been running for a while. We've got two threads, S and T, and they're both running the same block of code. So both of them start at A, calling B, and B goes into a loop, yielding over and over again. So A and B are procedures in an individual thread, and S and T are each threads, and both S and T will be running A and B. Everybody got that? Okay, and so here's thread S. And before we look at the horseshoe again, let me just show you something. Think for a moment if S was the only thread in the system, and all that yield did was like a null procedure. It saved and restored its own register, so it didn't do anything. Okay, so just think that for a second. And notice what would happen with this code, right? A calls B, B goes into a loop which says while true, call yield, yield goes into the kernel, comes back out again, you return from yield, you go back into the loop, you call yield, it goes into the kernel, it comes out again, and you loop. Okay? So if you think of that for a moment, then what happens on the stack? Well, A calls B, B calls yield, yield goes into the kernel, run new thread, calls switch, then switch returns, run new thread returns, yield returns, we go back into B, we call yield. And basically the stack is just going to go up and down and up and down. Okay, is everybody with me on that? That's just a standard serial execution, which you learned about in 61C, where we go down the stack, we go up the stack, we go down the stack, we go up the stack. Okay? Now, all that we did when we did this was we said there are 2 threads, and only one of them can have the CPU at a time. And therefore, what you think of as thread goes down the stack, and then when we switch variables from S for T, all of a sudden, it's like thread S is frozen in time. And what we've loaded is we've reloaded the point at which T was frozen the last time around. So we reload all the stuff with T, and now T goes up again. You know, return from switch, return from run new thread, return from yield, go into the loop, call yield, call run new thread, call switch. We switch them again, and now S has been frozen in time. We come back here, and now it's exactly where it was when we froze it, and now we just go back up the stack again. Okay? Does that make sense to everybody? So the way to make sense of all of this is for any individual thread, if a programmer had to worry about all the threads in the system and had to understand, to understand S, I got to understand that it's switching over to T. Okay, this would be chaos. No programmer would ever program a multi-threaded system. Instead, the way the programmer thinks about it is purely that S is the only thing running. And when you call yield, all that happens is I pause for a while, and then it exits from yield and I continue. That's all that the programmer has to worry about for S. It's also all the programmer has to worry about for T. It's the fact that we put the magic of switch underneath, which means both S and T are kind of going at the same time, that allows a diagram like this to be put up on the screen and only confuse you for the short period of time before you get it. Okay, but only the operating system needs to know what's going on in the inside. The programmer is really thinking still of a single thread doing its thing. Okay, any other questions on that? Does that make sense to everybody? Go ahead, yeah.
How did thread D get started? Did you assume that it was already frozen in time?
Yes, everybody wants threads to start somehow. I just don't understand. Well, so I'm going to tell you how they start in a few slides. To understand these two, I'm just giving you a hard time. To understand these two, this example, I wanted you to assume that they've been running for a while and we're just seeing them multiplexed. Okay, we're going to get to how T started and how S started in just a little bit. So you're going to have to suspend your disbelief that they could get started for just a moment. We'll start them, I promise. Any other questions? Okay. So what's today? We're going to start with a little bit more on interrupts because I want to make sure they make a lot of sense. And then we're going to talk about thread creation and destruction. And then we'll talk about building systems with more than one thread and having them cooperate with each other, which is going to start leading us down the path of synchronization, which is going to be kind of our next major topic for next week. Okay? I think I saw somebody go, ooh. Synchronization is not so bad. So let's talk about interrupts for a moment. So I kind of gave you this abstract notion of interrupts last time, but let me dive into it a little bit more. What is an interrupt? So an interrupt is typically a physical signal coming from some device, like here's a CD-ROM or a printer or a network card, and that interrupt is a wire that goes into the system, and when it's asserted, it says, I need service, and when it's not asserted, it says nothing. Okay? Now, whether these interrupt lines are level triggered or edge triggered varies from system to system, so whether it matters when it goes from low to high is the signal, or you just leave it high until it's serviced and put it low, that's going to be a little bit off of our radar for the moment because it doesn't matter so much. But notice that these three signals go into what I call an interrupt mask. Now, what is this yellow thing? So this yellow thing represents something that's inside the chip, a chip talking to the CPU. Now, this could be in the South Bridge or some other peripheral controller, or it used to be in the very old days of the IBM PC, this was a separate chip. But the bottom line is this is some hardware. And what is the interrupt mask? Well, the interrupt mask is basically a bit mask that says which of these interrupts can even bother the processor at any time. So if you got a 0 in the mask, then it doesn't matter what happens on the interrupt line, it's ignored. Okay? And then suppose we have an interrupt mask which allows basically signal from, say, the CD-ROM, the printer, and the network here, so there's 3 ones. Then the problem is it's possible that simultaneously we get 3 interrupts at the same time, and then what? Well, now we got to choose one. So typically there's some sort of priority encoder that will choose amongst the interrupts that have actually been selected. This thing is not as important as you might think, because most of the priority we're going to talk about is in manipulating the mask, and this is kind of for those instances where a set of things are simultaneously asserted which are considered to be of the same priority from the operating system's standpoint, and it's just a matter of picking one. So what this priority encoder does is it picks the interrupt, turns that into an ID, and hands that off to the CPU. At the same time, it maybe gives an interrupt signal. So what is this ID? This is some number that says, 02 might be the printer. Okay, and this interrupt line is basically telling the CPU that there is an interrupt that you should service, and by the way, here's its number. Okay? And then what does the CPU do with that? Well, the CPU, assuming that it's receiving interrupts at all, will basically stop what it's doing, go off and run an interrupt routine which depends on what this ID is. So it might actually run a different interrupt routine for the network and a different one for the disk and so on. Now notice I've got this little interrupt disable bit inside the CPU register, and that will explain this slide which you saw last time, and I'll show you again. But if this bit says disable, then this interrupt is entirely ignored and the CPU won't look at anything. Okay? All right. Questions so far? Yeah.
If that is disabled, bit set, will you ignore the non-maskable interrupt?
If the interrupt disable is set, then you still do not ignore NMI, which is non-maskable interrupts. Because NMI is typically, power just died, you better do something really quick, you're about to go under. Yeah, question?
What's there a need for interrupt disable when you can just set the mask to 0?
I'll show you in a second. That's a good question. Why do we actually have the interrupt disable when we've got the mask set to 0? And I'll show you how those interact in a second. It's a good reason for that. The short answer is that it allows you software priority mechanism much easier, but I'll show you in a second. Okay, now notice also I've got the timer here. So the timer is something that you program to say how often it goes off, or if it goes off at a certain time and place, and that just comes in as an interrupt. I also show you this software interrupt notion, and this is a hardware software interrupt, if you excuse that terminology. What it means here is if I set some bits in my interrupt controller, they essentially assert an interrupt just like anybody else. But these bits get turned on by software. Okay. So I think I just said all this. So the interrupt controller chooses which request to honor, and that's a combination of the interrupt mask and the priority encoder. Software interrupts cleared by software. And the CPU can disable all interrupts with this internal flag. Okay, I think, and an NMI is basically a game over type flag, and so basically when that's asserted, the processor stops what it's doing and does something else. Yeah?
And all of the verbal things can be modified by software?
Yes. So typically everything in here is programmable by software. Yeah. Typically programmable only by kernel mode, by the way, though, for obvious reasons. Okay.
Does an NMI take priority over trap disable?
Yeah, NMI basically takes priority over everything. NMI is often used for extreme game over type scenarios like power. It can be used for uncorrectable memory error. There's several things that basically, it doesn't matter if you have interrupts disabled because whatever you're doing is about to die as well, so just try to do something. And NMI is usually a pretty desperate act. Yeah.
If you disable the interrupts and something fires like a timer, does that eventually go through?
So let's talk about that scenario. So suppose the timer's gone off, but we've got this guy disabled. Or we've got the net mask bet set so that the interrupt is not, so the timer doesn't get through. The timer won't get through. So what happens, though, when you re-enable is that typically at that point, the fact that the timer's there is recognized actually does go through and the interrupt goes off. Now, the bad scenario, of course, is you crash your system in a way that disables all interrupts and doesn't re-enable them. And sometimes things like the keyboard and a few other devices that you might actually want to have interrupts come through for, if you've disabled everything, then you can't even talk to the device to re-enable them, and you're kind of in a bad situation. Control-Alt-Delete at that point, yeah.
So when an interrupt comes through, it basically, the wire stays asserted indefinitely until the interrupt actually goes through, or?
So that's a good question. So let's not deal with edge-triggered interrupts because the level-triggered are more common. So what happens is, say the network has some service it wants, it will actually assert this line, and it will, as long as it's asserted and the interrupt mask turns it on and the interrupt disable's going on, effectively you're causing an interrupt to the CPU. And it's up to the CPU to go back and actually talk to the device and clear it. And so it will stay asserted until the CPU says, oh, okay, you're done with service.
So even if the mask is 0 or interrupt disable's on, the CPU still knows about the interrupt until it decides?
Yeah, well, if things are preventing the interrupt from getting through, then the CPU doesn't know about it. But assuming these are on, the CPU will continuously know about it.
Even with the interrupt disable?
With the interrupt disable on, the CPU doesn't know anything about it.
Like, say you get an interrupt from the network and the CPU disable bit is set.
Yep.
How long does that interrupt stay?
So assuming that,
Can the CPU just like miss it completely?
good question. So suppose we keep things disabled for too long, a network interrupt comes in and the CPU doesn't get it in time, and will it miss it? So the short answer is it won't miss it usually, because most devices won't deassert their interrupt until the CPU does it. So it's asserted in hardware, deasserted in software. However, the longer answer is, if these events are coming in at some rate, it's possible you'll miss the thing you are being signaled about, because the next packet comes in and it overflows a queue. So that's why you've got to be very timely about your interrupt handling, and you can't leave things disabled for too long. Now, let me go to this diagram I showed you last time. Hopefully this will make a little more sense. So here we're running some code, and an external interrupt comes in, and that actually causes a pipeline flush, while at the same time we go off and do what it's kind of like a hardware procedure call, where we save the program counter and we disable that one bit in the CPU so that all interrupts are disabled, and we go into supervisor mode. Okay, and the reason that can anybody tell me why I turn on the disable all interrupt bits at this point? Yeah.
So your interrupt doesn't get interrupted?
Yeah. The only way to prevent a recursive infinite interrupting of an interrupt is you got to turn them all off for long enough to correct something, right? And in fact, here's here's a brief sort of way to think about this. All interrupts are disabled in hardware, but then in software what we do is we raise the priority. And what does that mean? It means we change the mask to reflect we're running at some priority, and all devices of that priority or lower will no longer interrupt, and only the higher ones will interrupt. So it's purely a software concept. We can choose sort of this hierarchy of masks that represent priorities, and so then what we do is we get this interrupt in hardware. All interrupts are off long enough for us to at least turn off the mask bit for the interrupt that just happened, and then we re-enable all of them by turning that bit back on. So the question earlier about what is that bit good for, it's really a way to get atomicity during the interrupting process. Okay? And then we save all our registers, and we go run the handler, and then we do everything in reverse at the end, where we restore registers, we talk to the device, clear the interrupt, we turn off all interrupts again by disabling that guy, and then we run an RTI instruction, which kind of does everything in reverse, restores the PC, goes back to user mode, and we continue where we were. Okay. And the other thing to note, by the way, is that software interrupts don't have to be done in hardware, because at the point where we change the priority by changing the mask back, we could see whether a software interrupt is supposed to occur and cause it to happen if we wanted to. So that's a piece of information you don't have to internalize right now if you don't want to. Are there any questions about the basic ideas here? Okay, so if we're going to use interrupts to do something interesting, then basically we have to typically fit into a scheme like this. And, we talked about timers being used to cause our multiplexing last time. Well, what does the timer interrupt do? Well, some of what it does in here is it decides to force a yield on some thread that wasn't yielding. Okay? Good. Yeah, question? Yeah.
Sorry, so we do that pipeline flush as soon as we get an external interrupt, but can any instruction actually cause an interrupt of its own? So if you're flushing the pipeline, what if like the pipeline flush causes it?
So pipeline flush isn't going to cause an exception, but external interrupts are asynchronous exceptions because they happen kind of independent of where you are in the code. Something that would happen in the code is a synchronous exception. Okay, so a good example is you divide by 0. So that'll do something very similar, but it's caused by an instruction rather than an external event.
Okay, so you're set.
Yeah, but those are also do a very similar kind of trap into a certain part of the kernel. Yeah.
So once you go into the supervisor mode, you take care of, you map all the other interrupts as link interrupts again, and then you take care of an interrupt, right?
Right.
So does it take care of more than one interrupt at a time, or?
So the question is, once we've gone into supervisor mode, one of the things is we want to make sure that we take care of the interrupt that occurred for us, which is, notice here, this clear current interrupt means that we've actually serviced, say, the network, and now we clear that interrupt so that when we return, we don't get immediately re-interrupted. And the question is, do you handle anything else at the same time? You can. A great example of handling something of a similar priority would be if you have a very fast network card. I mentioned this last time. Packets are streaming in. In principle, you could have an interrupt for every packet, but what really happens is that would take too much time. So in this network handler, you actually say, well, I got the first packet, got me into the handler, but now I'll empty all the other ones out, and then I'll return. So if the question was, do I handle things unrelated to the interrupt I had, you can. That's a little less common, but it's possible. Yeah.
So once you do your pipeline flush and you disable all interrupts, you raise the priority, and then can you actually get interrupted by higher priority
Yeah.
interrupt?
So one notion of raising priority would be just disable all interrupts. So, but the reason you might have priorities is because certain things might be more important than others. And so, in fact, the idea of this raising priority is you only mask out things that are kind of a similar nature to yourself and same priority. That allows things of higher priority to actually interrupt you in the middle.
So if your interrupt got interrupted, it would do the second interrupt, then come back, finish your first interrupt, and then go back.
Exactly. So if the interrupt got interrupted, we'd do the higher priority one, return to the lower priority one, then return to the base level. Yep. Yes.
Wouldn't you want to clear the interrupts before you do the transfer from the network to buffer?
Well, it doesn't matter where. So assuming that clearing the interrupt might actually have some hardware effect like clear things out, you'd probably want to do it afterwards. But
Well, right, but if you were to copy everything that's in the packet buffer, and then the hardware writes more data, and then you clear the interrupt, and then you've lost it. Whereas if you clear the interrupt before you do the copy, then if the network then copies more data, you just get an extra interrupt.
so basically, you have a way of looking before you actually clear. You can look and make sure nothing else has come in.
And that's an autonomous operation.
Yeah, you can not have that problem that you're worried about. We can talk about this offline. But that's a good question. Yeah.
Since you can interrupt your interrupts, is it possible to lose the values of the register?
So
Save them off?
you need to. So you're worried about getting interrupted in the middle of this.
Sure.
So, however, notice that the registers you're saving kind of represent the state of this point. And so all that's going to happen if you interrupt by something higher is it's going to start saving at a different point, and when it restores, it'll be kind of exactly where you were before you started saving your registers. So no, if you caught that, it's not actually going to be a problem. Okay.
When you're in user mode, you want the interrupts to be enabled, right?
Yep.
So why do you disable them down from hardware?
Oh, so that's because we want to redisable all interrupts, which is turning that bit in the CPU on, so that we can restore the priority to what it was, which is change the mask back. But we don't want to catch any interrupts until we've successfully returned to user level. So this notion of disabling is turning that bit in the processor on to disable everything, but the return from interrupt will go back to the mode we started with that bit off. So that bit in the CPU, by the way, that's modeled after Spark. The different CPUs have different notions of that, but that's all, that one bit interacts very closely with both the interrupting mechanism and the return from interrupt mechanism. It's tightly bound. It's sort of, you know, here's how you should write an interrupt handler is typically in the manual somewhere for that processor. Okay? All right. I think we'll move on here. So if you remember last time, we talked about how to deal with threads that may not want to yield. Well, we just have the timer interrupt, force a run new thread in a switch. Okay, so no magic there. Okay, now the magic, of course, is making sure that, well, you have to deal with the saving and restoring of registers and all that sort of stuff, but that's just a little bit of detail. Conceptually, this is the fairly simple idea of the timer forcing a switch. Okay? Good. So, any questions on that before we go to Administrivia? Good. So, Administrivia, I mentioned last time information about subversions on the handouts page. How many people have actually tried to use subversion? Does it work? Good, good, good. Glad to hear. Every other term, we have some weird problem with the subversion server, and so I'm glad to hear it actually works. Also reminding you there's a bunch of things on the handouts page which will be particularly interesting to you guys next week as we start diving into synchronization, so there's actually some examples on there to play with. There's also previous midterms and solutions, and there are papers that I put up occasionally for interesting reading. I realize this may be the generation that no longer actually reads anything longer than a tweet, but there's actually some interesting research papers to look at. Everybody should be in a group. Is that? I think that might not be entirely true. I know we have one small group and possibly some stragglers. If that's true, you need to talk to Angela, who's our super duper group scheduler person, as soon as possible. And let's make sure, here, raise your hand, and she's on the information page, because we need to fix this. There may be a few of you that are in really big groups who we might see if you'd be interested in moving a member into a group that's missing somebody, because we want to try to stabilize the groups a little bit, and we need to do it soon. So, okay. Readers available? People been able to get it? Okay, good. Yeah. Once you know it's at VIX instead of Copy Central, that's a little simpler. How many people have started looking at nachos? Good. Okay. I see the rest of you guys have thought about starting to look at nachos, right? Yeah, okay, good. The other thing I say here is, at the very beginning, start figuring out whether your group has interactive issues, because it's good to fix those early rather than later. So start observing how your communication's working and start thinking about it. I think the TAs last time actually talked a bit about group interactions, I think. So there will actually be a whole lecture, lecture number 9, not a whole lecture, half a lecture, on ways of organizing your groups. But we're going to let you try it first to see how that works. But if you want a few hints, you can take a look at lecture 9. And speaking of which, there's some possibility that I won't be here on Wednesday the 29th, but I have convinced Eric Brewer to come over here and give the lecture. How many people have ever seen Eric Brewer or talked to him? So he's a very good lecturer, and the 29th is actually that lecture that's half about how to interact with groups. And what's interesting is Eric started a company in the .com craze and knows all about managing groups. And there was one 260 or something that he, or maybe it was 269, whatever, that he actually brought in real management to help manage groups, which was kind of interesting to see how that worked. But so he'll be a great lecturer on that topic. If it turns out I can't make it here, so we'll still have class, but I apologize in advance. Any other Administrivia questions? Yeah. Should be up on the lectures page, is it not? I think it is. Yeah, it should be up on the lectures page. It's somewhere in mid to late October, I think. It's up there. On the 18th. There we go, mid to late October. So by the way, just on that topic, when we have midterms, there won't be any class that day, but I'll have office hours during the day. My normal office hours start at 2:30, so I'll probably go from 2:30 to 5:30 or something on that day. No, the office hours will be, where will be the exam? Don't know yet. It'll be somewhere bigger where I can, in theory, spread you guys out a little bit. So. Yeah, so it lies. I don't actually have it scheduled yet. I should remove that. Thanks for pointing that out. Oops. It was in there. It was in 145 Dwinell last year. Okay. Any other questions? Okie doke. Good. So, if you remember, we talked about this little diagram of the life cycle of a thread. You know, it goes from new to ready, and then it goes to running and maybe waiting and terminated. And pretty much we've been talking about the ready, running loop over and over again, right? That horseshoe diagram was kind of two threads. They've been running for a while and they're alternating. And the thing that we haven't done is we haven't really talked about how a thread starts. And I know you're all anxious to know how threads start. I've heard that. I hear it in your voices, especially with the questions that keep coming up. So let's talk about this. So we're going to talk about something roughly, I'm going to call thread fork. Okay, so the forking idea is basically we're going to create a split in the execution. There's going to be two separate threads when we're done. And this is an old Unix term. It's been around for a while. And it's a user-level procedure that creates a new thread and places it on the ready queue. Now, it can't be entirely user-level because the notion of placing on the ready queue is a kernel-level concept right now, right? Because the ready queue is inside the kernel. So let's figure out how this might work. So what are some arguments to thread fork? Well, certainly you need to tell it what routine to run, okay? Because you're going to run a thread on some routine. So that's probably a pointer to the application routine. It's quite possible that the thing you're going to run needs arguments, so there might be a pointer to a bunch of arguments. And, of course, there might be the size of the stack to allocate. So we're going to kind of take the easy road here on how to figure out how big of a stack to make, and we'll just say that you who are creating a thread say how big the stack is. Okay? Now, how do we build this? Well, first we got to sanity check all the arguments. And the reason we sanity check all the arguments is that it's possible that you've got some weird bug in your code, and we want to make sure that we catch that bug early. And I actually say we sanity check the arguments, we enter kernel mode, and then we sanity check the arguments again. Can anybody tell me why I'm enforcing such sanity in the picture here? Yeah. Yeah, you know, once getting into kernel mode, though, is an atomic operation, so they can't really change it in the transition period. Now, maybe you're checking one thread getting screwed up by another thread, is what you're thinking?
Well, you sanity check the arguments in user mode, and then you time slice to the next thread.
Yep.
The arguments, time slice back, and then make the call to enter kernel mode.
Yeah. So you're thinking about two threads interfering with each other. And for now, our security model is that two threads can interfere with each other. That's just kind of the name of the game. So we're not going to try to protect against that. Can anybody think of a different reason why we might sanity check twice? Yeah.
So maybe the kernel can see something that at the user level it couldn't see, and so it has more knowledge of what's the same.
Yeah, possibly. So which one of these two sanity checks is most important for security? The kernel mode. Okay, so clearly this one is there because once we've entered kernel mode, now the thread can't really do anything bad, and we want to make sure that it hasn't suggested to us that we run some routine in the kernel somewhere weird, or given us a null pointer to go chasing down or whatever. So this sanity check is really making sure by the kernel that the user thread that is creating this other thread really has permissions for all the arguments. This other sanity check is kind of optional, and it's really here to make it easier for a user level debugger to help the user, because we're still running at user level. We sanity check the arguments. Maybe there's something weird we say, we can jump to a debugger and say, you did something pretty weird, and we're still in user mode. Okay? So that first one is kind of optional, but might help you with debugging. So once we've entered kernel mode and we've made sure that we have good arguments, now we have to create a new stack and a TCB, right? Because we're making a new thread. It needs a stack. It needs a thread control block. We're going to initialize the thread control block. We're going to place it on the ready queue. And we're done. Okay, so that's all easy, right? So now everybody who was asking questions about how the thread T started, they have no more questions, right? All right, maybe you have some more questions. So let's talk about initializing the TCB in the stack, okay? So what do we initialize in the TCB? Well, first of all, we better have a valid stack. So we need to point the TCB at the stack, okay? And what's kind of going to be interesting is we don't have to initialize all the registers. There's going to be a little bit of magic that I show you here now. We're going to take and set the PC return address register in the thread control block to an operating system routine called thread root. Okay, it's going to point at thread root. And we're going to have a couple of argument registers, A0 and A1, initialized to the function pointer and the pointer to the arguments. So notice that inside the TCB, remember there are 32 registers, let's say, because of MIPS. We've only initialized 3. We've initialized R31, which is the return address, and we've initialized A0 and A1, which are R4 and 5, I guess. And that's it. And the stack pointer, 4 registers. And do we initialize the stack? No. Because the important part of the stack frame is in registers, namely the return address. And so think of the stack frame that we've just created as being kind of just before the body of thread root really gets started. So it's like, here's our stack frame, and we've got this thin little thing that has no actual data on it, which is our thread root stub. Okay, and that is a brand new thread that hasn't actually executed any cycles yet. Now, let's see how we run with this. Okay, so let's take a look here. Here is a thread that's been running for a while. And notice that I've actually, this is just like thread S earlier, but notice that I have this little thread root thing at the top. And so the first thing that you should notice about this as different is A, which was the first procedure called by the thread, actually has been called by this thread root procedure. So thread root is really the root of the thread, surprising to everybody, right? And it calls A, which calls B, which calls yield, and so on. Okay, so the only thing we've changed about S so far is we've added a thread root at the top. And let's take a look at what happens when we switch. Okay, so we're going to do exactly the question earlier. What happens, how does T start? We're going to assume S has started, but how do we start T? And notice that here's S. We come down, we hit switch, and now we're going to switch to this little TCB that we've just initialized 4 registers in. And what 4 registers? Well, we switched to a new stack, right, because the stack pointer was in there. We've switched to having A0 and A1 be the pointer to the function and the pointer to the arguments. And the return address for thread root stub is actually set to a routine called thread root. So remember before, when we switched into, let's just go backwards, we switched back this way, the first thing we did after switching is we returned from switch. Here, the very first thing we do is we switch over here and then we execute return. But what is return pointing to? Thread root. So the very first thing is we switch the registers and then we execute return, but return then causes us to start running the thread root code. And as a result, it's like, poof, we're at the top of T, but right here. And we did that because we hit the return. Okay, so think about that for a second. Are there any questions? Yeah. Oh, yes. That's a great question. When we get over here, is the PC looking at something that looks like return? And the answer is yes. Can anybody tell me how they know that for a fact? Because we were busy executing a long switch, right? And we got to the point where switch is about to return, and then we did the switch, and the very next thing that was going to happen was execute a return instruction. So it's actually the return instruction kind of from over here that we're going to execute. Don't ponder that too long, though. But in principle, we're going to switch over, and then we're going to return right away. Okay? It's the last thing that switch does while executing. Because remember, switch is just a piece of code, right? And all that code does is it saves out some registers, loads some other ones, and then executes return. That's all that it does. And so while we're executing this routine, we save registers, restore registers. Now our stack's over here, and then the last thing we do is we execute that return, and that causes this guy to execute. Okay? Yes? Yeah, so thread root stub is the stack where nothing has executed yet. And so all it really is it's like an empty stack plus the TCB had the return address register pointing to the thread root routine. So you could think of it, the point that we are here, we've only executed as far as the beginning of thread root, and we're about to go farther by executing the return routine. Whereas once we start executing thread root, then we have a full procedure that we execute. Okay, and here's that procedure, by the way. So what does thread root look like? It does some startup housekeeping. It switches to user mode. It calls the function pointer on the arguments, and then it executes finish. Okay? So what is the startup housekeeping? Well, I don't know, includes things like start time of the thread, other statistics. Okay? And so as we're executing this thing, we return kind of to the head here. We do our housekeeping. We switch to user mode. Now we're here. We call the function code. And now, in the middle of this is where we were before, where we're executing S&T all the time. And then finally, when we're done, we execute finish, and the thread is dead at that point. Okay, there you go. Thread just started. Questions? Yes.
Does it get lost in waiting queue somewhere? Is somebody waiting queue?
You mean the thread that hasn't started yet?
The thread that was put into a waiting queue.
Oh, so any thread. Does any thread ever get lost in a waiting queue? Well, if there's a bug in the kernel, yes. You could have a thread go to sleep and never wake up. But normally, the wait queue has some way of waking it up, so it should be the answer is no. Okay. This seems like a great point to break. Let's take about a 3 or 4 minute break and relax, and let's get the door open because it's dying of heat in here. See you back in a moment. Unfortunately, all of our chairs are up top there, so we can't prop anything in it. Is there a foot or anything? Oh, put the garbage can in here. Wow, opening the door really helped in the heat here. Okay. I had a really good question up here during the break. Somebody said, so why is it that the stub, you have the return executing on the stub? Why don't you just have the PC set to the thread root? Okay, because in theory we're saving and restoring the PC, right? I said that multiple times. In fact, if you look really carefully at the switch code, we don't actually save and restore the PC. The PC is never saved and restored in the way I've shown you this code. What actually happens is switch saves and restores the registers, which change the stack, and at the very end of switch it executes a return. So the return that causes us to start thread root is actually the return over here in switch. Okay? There you go. That'll screw you up for a while. Ponder that. Okay. So let's talk about thread finish. So what's kind of interesting here is thread root represents the whole routine. That's the thread right there. This is the whole thread from beginning to end. When thread root exits, the thread is dead. Long live the thread, right? So notice we do some stuff in the kernel to housekeep, which maybe takes some statistics. We turn into user mode because threads all run in user mode, and we started in the kernel. So that's why we went from red to blue. We actually execute our routine, our function. When that function returns, we execute thread finish, we exit thread root, and the thread is dead. Okay, so that's the complete life cycle of a thread right there on the screen. And that, of course, leads to the question, what the heck is thread finish? And so one of the things, to kill a thread, we clearly have to re-enter kernel mode, right? Because we're going to change the TCB, and we're going to remove it from all waiting and ready queues and so on. Okay, so we have to get back in the kernel, so it executes a system call. And then, listen carefully, it needs to wake up all the threads that might be waiting for it to finish. Okay, this is often called join. Okay, so you join the thread, and when the thread dies, then you get woken up again. Okay, so part of our housekeeping is saying if anybody was waiting for us to finish, notify them. And then you can't quite deallocate the thread yet. Can anybody figure out, without looking at my slides, why that is? Yes?
Maybe have children that you finish.
Well, the thread here has basically given up the ghost, so it's not like we can wait for any children. But when I say can't deallocate the thread, I'm really talking about the thread control block and its stacks and so on. So why, yeah?
Return value?
What about the return value?
Needs to still be around.
Why?
Another parent for someone else to get at.
Not quite. Yeah.
Will the queues for getting that thread?
No. Yeah.
Thread can't destroy itself while it's still running.
Yeah. So if you look, what does it mean to be running thread finish? Well, we're busy executing on the stack. And so if thread finish were to deallocate the same stack it's running on, chaos would ensue. So in fact, what we need to do is we need to switch out of this thread into another one and let a different thread deallocate us when we're no longer running on our own stack. Okay, remember the notion of zombie processes that I brought up a while back? So this is kind of where they start showing up. Because you go as far as you can in finishing yourself, but you can't quite finish because that would involve deallocating yourself while you're running. Okay, now I know that probably happens when you've got a little too much coffee at night. You deallocate yourself while running. But you can see that, yeah, you crash. That doesn't work too well, right? So that's exactly why we can't just deallocate the thread. So we're still running on its stack. And instead what we do is we kind of record the thread with a little flag that says waiting to be destroyed. And what happens in a kernel that shows you a whole bunch of zombie processes is something that's supposed to be cleaning them up isn't working. So somehow that process has gotten frozen somehow. And usually, oftentimes in systems I've dealt with, the only remedy there is reboot. So what happens, so thread finish has re-entered kernel mode, woken up any threads that are waiting for it to finish, and then it executes run new thread. So it picks a new thread, calls switch, okay, and then calls thread housekeeping, which at that point we're running on a different stack, and we can basically notice that waiting to be destroyed is there, and we can deallocate the thread. Okay, so we've had to actually switch into somebody else's stack and then execute thread housekeeping, and then we're done. Okay. These are the little magic. So, by the way, you know, up until now, you've all had this nice little abstraction of, you know, a thread executes straight through and it's done. Now you're getting to see why it's not quite so simple once you dive into the kernel, right? The work we have to do to give us the abstraction of threads executing in parallel is a little tricky. So, you've just been initiated into trickiness here, okay? So, the way I'm describing it here, thread fork is not quite the same as Unix fork, because Unix fork actually creates a new process. So it has to create a whole new address space, and we've been only dealing with threads so far, so processes are not our worry. Thread fork is kind of like an asynchronous procedure call. Basically says, oh, okay, here's the thing to run, go do it. And I don't wait for it to finish, I go on and do what I was doing. Okay? Now, what if the thread wants to exit early? Okay, so those of you who have ever programmed in C probably know about the exit system call, okay, which you may have executed. Essentially, thread finish and exit are about the same thing. Because thread finish, the first thing it does is makes a system call to get into the kernel, and that's the same thing exit does. So thread finish and exit kind of are the same thing. So if you look back here at this code I showed you, it's kind of like do this, do this, do this, execute exit. And if you happen to execute exit in the middle of your function, the same thing happens. Okay. Now, one thing that is kind of interesting is if you know how to use PSAUX or you know how to use your task manager in the right way, you can actually notice that there's a parent-child relationship between processes or threads, which kind of often start with thread 0 or process 0, depending on whether you're looking at threads or processes, and they each have kind of things that they have created. And so the children of the init process is a set of things, and then these have children, and so on. And what's kind of interesting about this sort of parentage tree is that certain of these processes are extremely important. So for instance, if you kill the init process, you reboot the machine. But this parentage is also kind of makes a little sense, right? Here's a C shell, which is calling ls and cat. Okay, so these guys are children of CSH. Okay. So now let's talk about thread join. So what it basically says is I'm running along, but now I want to wait for somebody else to finish. And so what thread join does is thread join takes a thread ID and it says, take me off the run queue and put me on the wait queue for that thread. And don't wake me up until that thread finishes. So think of it this way. You've got two threads running. I say join with this thread. I go to sleep. And when this one is done, then I wake up again because we've joined together in some sense, because the one that I'm waiting for is now dead and there's now only one of me. Okay? So this is a very important kind of thread synchronization idea. You can certainly see where that might be useful if you've got a lot of this parent-children relationship. You can imagine that, in fact, you might have the parent wants to wait for children to finish, and so you'd join on the child processes, and when they finish, then you'd wake up again. Okay? Now you get to actually implement join in Project 1. So where's a logical place to store the wait queue? How about in the TCB of the thing you're waiting on? Does that make sense? So if I join with some thread, what that really means is I get taken off the ready queue because I'm not running anymore, and I get put on his wait queue. And then what happens with thread finish is it wakes me up, because thread finish for this thread goes and wakes everybody up on this queue puts them back on the ready queue, and now they're running again, and this thread can finish its termination. Okay, any questions on what join means here? Does that make sense to everybody? So here's an example of a wait queue that's not even kind of in the kernel proper, so to speak. It's actually in the TCB. I mean, that's in the kernel, but we sort of, in principle, every thread can have its own wait queue of people waiting for it. Yeah?
Wait for a thread to yield, or
Usually there isn't an interface to wait for a thread to yield. Because remember, yield is basically purely there. You maintain the abstraction of the thread doing its thing, but yield just says it gives up a little time every now and then, but it's not actually done. So usually you usually don't have that interface. So why might that be useful?
if you were waiting for a certain piece of the work to be done, but you're not.
Oh, if you're waiting for a certain piece of work to be done, you wouldn't use yield for that. That's a great question. That's synchronization. So we're going to talk about that next week. Because if you've got two threads doing something and you got to wait for one of them to finish, then you want to synchronize with them. That's different than yielding. It's exactly a type of synchronization. Thread join is a type of synchronization, but thread join only works when the thread's completely done. Whereas what you want to do is you want to synchronize part of the way through, and that will be next week. Promise. Okay. Any other questions? All right. So, the wait system call in Unix, and there's wait 2 and 3 and 12. Now, there's a lot of different variants of wait, which are all about waiting for somebody to finish. Do a man on wait sometime. You'll see it. So let's take a look. Oh, yeah, sorry. Go ahead.
Oh, so you couldn't have a thread that wants to say it wanted to compute something, and so it wanted to make two different threads to compute the
Yep.
subparts. You can't make them make them both and then thread join on both of them, because the first thread join would stop it before the second. Right?
So you create two threads, and you want to thread join on both of them. Well, the problem is, yeah, you're right. The first one you thread join puts you to sleep. But you could wake up and then thread join on the other one afterwards. Which, by the way, I've just given you a hint at a type of bug you got to be careful about when you implement join. Because what happens if you go to join a thread that's already done? Think that one through. Okay. Any other questions? Now, so traditional procedure call is kind of logically equivalent to a fork followed by a join. You ready for some silly code? So A calls B. B does some interesting, complicated stuff. Okay? Look at procedure A prime. We thread fork B with no arguments, because B has no arguments. We get a thread ID. We call thread join. Okay? So A prime is logically the same as A. Why is that? Well, the parent A creates a child that runs B, but then we join, so that then the parent goes to sleep until this thread is done, and we know that B is done, and then we exit the thread join, and it's just like we called B. Okay? Kind of silly, though, right? What's silly about that? Yeah. Yeah, we're wasting a lot of creation and join overhead in this instance, but it is kind of, I like this equivalence as a way of kind of understanding what it is that fork and join do in this circumstance. Normally, why not do this for every procedure? It's just too much work. Normally what happens is you use this kind of thing where the parent is going to continue to compute something here while B is computing in parallel, and then we join at the end. That would be why you do this. So you do this to put something in the middle there, right? And, context switch overhead, memory overhead for stacks, all that sort of stuff is a reason you wouldn't do this for every procedure. Yeah, question?
Is there a way for A prime to get the return value from B in this thread or thread join?
Yes, there is. In fact, typically,
Would it have to be message passing or shared memory?
no, actually, so the typical wait system calls actually have a way that you can get the return value back. So, fact, we might even ask you to do that in number 1, lab 1. Okay. So let's talk a little bit about kernel mode versus user mode threads. So we've been talking about kernel mode threads. Native threads supported directly by the kernel. Every thread can run or block independently. The kernel has the ready queue, it has the run queue, it's doing all this scheduling. Okay? One process could have a whole bunch of threads in it, the way we've been talking about, and each of those threads could individually be asleep. So process creates 20 threads, and each thread does I/O, and so some of them could be sleeping, some of them could be running. That's just fine. Okay? Nothing we've said here prevents that. Now the downside with kernel threads is they're a little expensive because you have to go into the kernel every time you want to schedule. So every time a thread gives up its schedule to another thread, you have to enter the kernel. Okay? And so that's a little expensive, and that actually led people to start asking, well, what, does this kernel switching actually have to happen, or does this thread switching actually have to happen in the kernel? And if you think about it, the registers we're saving and restoring are all user mode registers, right? Because they're things that the user can write. I mean, your program writes the registers, right? So why not have your own program keep its notion of TCBs at user level and do its own switching every now and then? Are we with me? Now the downside of this, of course, is that it's a little trickier to get interrupts, and so having timers wake up part of the user level threads to schedule them is a little tricky, but you can certainly do yield this way, where yield calls a user level routine which then switches the TCBs. You could do all of that stuff at user level. There really is nothing that I've described so far other than the timer interrupt that requires the kernel. And in fact, this led to a whole bunch of different implementations of user level threads. So there were originally there was something called green threads, and then there were a bunch of these other ones that were developed. And the idea here is that you've got kind of the thread, and I say that in big caps, which is the thing the kernel knows about, and that thread has a bunch of its own little lightweight threads that it's switching between. Okay, so the thread is the only thing the operating system knows about, and the threads are up here running in user level. They're lighter weight. And, you know, that's fine. It works great until one of these lighter weight threads makes an I/O call and puts the whole thing to sleep. Right? Suppose I got 20 threads, they're up running, and one of them does disk I/O, and what it does is it puts the whole big thread to sleep. Now I know where they got droid from. And as a result, none of the threads are running anymore. It's a conundrum, right? So user-level threads have this problem that they're cheap and lightweight, but maybe they don't work well if you block on them. Okay, so when one thread blocks, all of them block. Kernel doesn't know anything about the threads that are up there, and so it can't really adjust the schedule. And so just one final thing here, and I'll answer your question. People loved user-level threads enough that they came up with some interesting options, and one of them was something called scheduler activations, which just Google it, you'll find lots of research papers on it. But the idea was that when you're doing user-level scheduling, if one of them goes to block in the kernel, the first thing the kernel does is gives back the thread via another up call so that you can continue to do the lightweight stuff. And so the kernel has to participate. Question?
That was my question.
Oh.
Somehow being able to, if a green thread blocks, being able to just sort of only put that thread to sleep and still have all the green threads.
Yeah, and what it is the kernel cooperates by knowing you're doing this, and it gives you back an activation in which you can continue to do your user-level thread scheduling. Yeah, good. So, you know, once you allow that, then you can kind of think of the threads as being these things down here, and then here's the one user-level thread to one kernel thread thing, which is kind of what we've been talking about up until now. But then you could have many threads with one kernel thread, or this is actually an even better solution where you have a few kernel threads and they're all working together to multiplex a bigger set of user-level threads. And so you don't really have to worry about this much now, although it's fun to think about. I will tell you the following, though, that this kind of an option is something you might use a user-level library for that would take care of the details, and it would give you threads that are very lightweight, and much lower overhead than, say, this model. And you would think you're still programming in this model, but the library would hide it from you and it'd be a little bit lighter weight. So this is typically something you bury in a library, and you as a user don't have to worry about it. You as a kernel writer might have to worry about it, but actually not even that right now. Questions? So I'm going to finish up. We have a little time today, so I want to talk about some meta issues here for the end of the lecture. So remember some definitions. So multiprocessing was multiple CPUs. Multi-programming was more than one job or task or process. Multi-threading was typical more than one thread per process. So what does it mean to run two threads concurrently? And what it means, remember we were kind of distinguishing concurrent and parallel. I sort of gave you this definition early on. Let me bring this back. What it means is if two threads can run concurrently, it doesn't necessarily mean they run at exactly the same time, but it means they could in principle be interleaved in some arbitrary way. And so you've got to treat it as if they are running at exactly the same time, because that's the only way to get the thing to work correctly. And it means the scheduler is free to do a lot of things. It can run the threads in any order, it can do them FIFO, random, etc. And if you have two concurrent threads and something that you do assumes the scheduler is going to behave in a certain way, you're likely to have introduced a bug. Okay, so for instance, here's multiprocessing where you know they're running for sure at the same time. Here is a couple of different multi-programming examples. Like for instance, maybe A runs to completion, then B to then C. I'll tell you that if you forked off 3 threads, I bet none of you thought of this as an option. Okay, but this could happen. And sometimes if you write code where you think they're making progress together and the scheduler does this for some reason, it may be that you get deadlocked or something. Right? Or the scheduler could do this where it runs a little A, then a little B, then a little C. This is probably the one that you would normally have thought of if you put 3 things running concurrently on the same CPU. But, you know, there's an infinite continuum of options in between here as to what would happen. So this kind of leads to some interesting questions. So if the dispatcher can schedule your threads in absolutely any way, you got to make sure your programs work no matter what it does. So you could think of the scheduler as almost like this malicious thing in the OS that's going to find the one interleaving case that screws your code up. Okay, it's you against the scheduler. And can you test for all possible options? Well, no. Well, it's hard. Okay, what you can do is you can test for all possible combinations of 2 breaks between threads or 3 breaks between threads. And people actually have validation software that will say, well, you've got these set of threads, and assuming no more than n context switches, is there a bug? But unfortunately, then n plus 1 comes along, and maybe you didn't catch that bug. So it's very hard to test, and it's also very hard to know if your program's correct if you're an undisciplined programmer. So what's going to happen, hopefully, in the next week or 2 when we talk about synchronization is you're going to learn how to be a little more disciplined about how you write multi-threaded code so that it's more likely to work. Okay, and I'm being optimistic there, but we'll assume it's more likely to work after you learn what we teach you next week. So let me get your heads around this for a second, though. So one option is if the threads are completely independent and not sharing anything, then this is deterministic. It doesn't matter what the scheduler does because neither of them are sharing state, and as a result, the interleaving doesn't alter what they do. Okay, so that sounds good. The nice thing is that's deterministic, so you could run it multiple times, you get the same result, so it's reproducible, and maybe you can actually debug it. Because now, the real world, we got cooperating threads. And in this case, there's shared state of some sort, like they share a file, or they share some variable in memory. And of course, what is that? Well, that's non-deterministic because the scheduler is not your friend, right? So they can do anything it wants to screw you up. It's not reproducible. You run it twice, you get a different answer. Okay? And non-deterministic and non-reproducible means that bugs can be intermittent. So what is that called? Heisenbugs, right? Okay, these are the bugs where you go to look at them and they disappear on you. Okay? So interactions really complicate debugging. And unfortunately, if you think about it really carefully, that this nice notion of truly independent threads really never exists, because at minimum the threads share the same operating system, and that's a single point of failure that can screw you up. Or they share the same file system or whatever. Okay, so the truly independent threads probably aren't really there. Okay, but often you can maybe assume that. A good example is a buggy device driver causes thread A to crash because thread B goes and accesses something. So you probably don't realize how much you depend on reproducibility. So for instance, an evil C compiler modifies the errors, the files behind your back, inserts errors into the C program unless you insert debugging code, and then it removes the errors. Okay, now, that would be very hard to debug, right? Or a debugging statement you put in overflow the stack. Okay, these are all examples of things that you really don't want to encounter. Well, I hate to tell you this, that when you have multiple threads running and they're cooperating, you start getting things that have behavior like this. Okay, so non-deterministic error is really difficult to find, and you know, depends on scheduling, which depends on the timer, which depends on other things. And original Unix had a whole bunch of non-deterministic bugs, and they've slowly gotten rid of them over time, and then they went to a different version which introduced a bunch of bugs, and then they slowly got rid of them. Okay? And you know, one example of non-determinism which people use all the time is typing to generate a key, right? Because there's enough randomness in the way you type to be interesting. All right, so let's end for now. So in conclusion, we talked about interrupts for some detail. Today, it's basically a hardware mechanism for returning control to the operating system, used for important and high priority events. And it's also a way to force the dispatcher to schedule a different thread. We talked about new threads and how thread fork works. Okay, and this is kind of magic. You create a TCB with a small amount of information on it, and you put it on the run queue or on the ready queue, and the right thing happens the next time it gets switched to. We talked about thread join, which is the first type of synchronization. It's the simplest type, which is wait till something's done. Next week we do more complicated synchronization. We talked about threads being at user level or kernel level, and we finally talked about Heisenbugs, which will plague you for a while. Hope you guys have a great weekend. We'll see you on Monday.